So we're going to begin with all of those nasty things that we had to deal with on the last test. So you can kind of hopefully get some of those issues answered and clarified and everything. You got the handout in back. We're gonna grind through some really fun problems. And the other twist today is it's Friday, and we're having some visitors come from a high school in San Jose. I don't know why they're coming down to NPC, except I think we have a couple programs that maybe are unique, so they're going to check them out. Football program, yeah. It's definitely our football program. But I think the high school has an electronics academy too, and so the counselor's going to bring them here. So because I'm teaching circuits, but we have to finish this stuff before they get here. But I'm gonna what I thought we would do is there's some really I've been onto this. Well, I'll share it with you at the time. But there's I think we're going to do a little competition between you guys and the high school students. It'll be a design. It's a design problem. We'll see if they actually know anything, and you guys should know this. It's really basic DC stuff. So anyway, it should be kind of fun and hilarious, and it's at 12:40. They're supposed to come at 12:40 today, but they're probably going to be late. You know how that is. So you may be able to slip out before they get here. But if you're here, and if you want to stay around and maybe talk to them about what you're doing about engineering, that might be really nice. It's the San Jose High School. I don't know which one. Then you want to leave before they get here. At 2, right? Yeah. Yeah. I'll tell them you guys all chickened out. So anyway, I'm glad you all solved example 10 yesterday. That was the this one that you're looking at right here, and here's the solution. And you kind of got to stumble through all the math involved with complex numbers. And the point being is, at a certain point, you have to kind of just give up with the calculator approach. As the problems get more complicated, you're kind of you're forced to. And I think this is an interesting transition in engineering, because up till now you've been doing everything in all your classes mostly on your own paper and stuff. But now it just gets to be so complicated that you need more computational help. And so we're going to be driven more towards using MATLAB to solve this. And this shows you how you might solve example 10 using MATLAB. If you don't have that ENG function that you downloaded, you could say, well, VG is this, and of course with the cosine angle of 0, that's 64. You can define ZC as this, and you can get the answers, from these calculations, and then you can plug those things into future calculations and come up with, the phasor VO and the magnitude and the phase angle of VO. But it's actually better if you're using free MATLAB to use your variables again. So if you define ZC here and ZL here, you can actually define Z parallel, and you can just use these variables in subsequent computations, right? So if you define what ZL is, and the parallel combination of this thing here is just ZL in parallel with the 2K ohm resistor. And so when you're actually solving it, you can say, well, you can make a new variable, ZP is 2000, that's R times ZL over 2000 plus ZL, and it handles all that complex math for you. You don't have to worry about all that J's and everything. It's all built into that because ZL has a J in it. The answer for ZP comes out automatically in complex form. And then you can use ZP by saying VO equals Z parallel times VG over Z parallel plus ZC. And again, it's just a voltage divider formula with 2 impedances. That's this thing. So it's Z parallel times VG over Z parallel plus ZC. Right, and so that's how you can really make a much better use of your time by using FreeMath to take care of all the number crunching for you. Okay, and then at the end you convert that into polar form, and that's your phasor solution. Even better, if you're comfortable with this, you can actually write a script file. See, this is actually just doing all this at the command line. And if you make a mistake, it's kind of hard to go back and fix it when you're working on the command line. But and we're going to do this in the lab on Tuesday. But all this stuff is here on the PDF. If you want to actually just see how that works and kind of play around with it, you can. But you can make a file, a separate file that actually has your solution in there. So you can define your omega, your inductance, your capacitance, your resistance, and convert to the phasor domain, define VG, ZL, ZC, do your circuit calculations, and put little comments in there explaining what this is doing, you see, and the voltage divider formula, and showing the results. And that's a much neater way of doing it, right? You can read that a lot better later on. If you want to see how did I do this, you can kind of read your solution that way. It's much nicer. But you can work with FreeMat in any of those ways, and it's still useful for you. And then your program output just looks like that. And we've already downloaded these functions last week, so you know where to get them. They're on the website. You can download those into your folder, workspace, and point FreeMat to that folder and use them. This just kind of shows you what mag phase does. You already know this stuff. This is actually the contents of the functions, in case you're curious. Those of you who are in Engineering 17, this is actually what's inside the angle function. The ang function takes a theta in degrees, computes the complex value just by doing Euler's formula. And the mag phase command uses the fprintf command to print out the magnitude of the number and its angle using the format string defined here, which is all kind of familiar to those of you who are in MATLAB. Yeah. So, sorry. It's programming, you know. It's all very similar. Yeah. Very similar. Anyway, as we've been learning, when we now are going to solve these AC circuits, the better way, the easy way to do that is to transform the circuit into the phasor domain, also called the frequency domain, and then solve for all the variables in the frequency domain, and then convert your solution back to the time domain. That's the preferred way now of solving these. It's just much faster. And now we're gonna apply this to solving more complex problems using things like nodal analysis, mesh analysis, and all that. Okay, so here's the problem. This is on your handout. This is example 1, and it's a complicated problem, you know. So how are we going to actually do this? Well, step 1 is going to be it's always step 1 is we're going to do what? Yeah, we're going to convert to the phasor domain, right? Yeah, we're going to do that. First step is converting into the phasor domain. Right. So we're going to say convert to the phasor domain. And we take note of all the important parameters. What's the most important thing if we're going to convert to the phasor domain? What do we need to know? First thing we need to know if we're converting to the phasor domain, most important quantity. Yeah, what's omega? Okay, and what's omega in this case? 1,000, right? 10 to the third. Ah, good. Good that way. Yeah, just never say anything. That way you can't make any mistakes. There's a saying: rather be quiet and thought a fool than to speak and be known as a fool, or something like that. And be confirmed as a fool. So if omega is 1,000, ZL is, as you all know, J omega L. Good. And that means that is J times 1,000 times 0.01, which is J10. ZC is omega C. Yep. And that's minus J over 1,000. And C is 50 microfarads, so that's 50 times 10 to the minus 6. And if you work that out, that works out to be minus J20. Okay. We can also find that, this guy. So what we can do, in fact, what I've done in this circuit is I've redrawn the circuit in the phasor domain. Whether you want to or not, I mean, this is kind of optional, but it can kind of help you visualize things. If that's initially that can be helpful, but after a while you'll realize, oh, it's really not that big of a deal. But if you're going to redraw this in the phasor domain, the resistor stays the same. The source has become what? What's the phasor equivalent of that source? Sorry? What would I put here by the source, this voltage source? Yeah, 10 angle 0 degrees. Good. That's the phasor transform of 10 cosine of 100 of 10 cubed. And notice where I had a capacitor up here, I'm replacing that with a resistor with a resistance of minus J20. to emphasize that it is like a resistor. It just has a, you know, a complex value. And then I'm going to replace this dependent source here with the phasor transform of 4 little I0. What's that going to be? It's the phasor transform of 4 little I0. Wild guess. It's 4 big I0. You thought it was a trick question. Yeah. That's right. You were right. Okay. And the inductor becomes J10, a resistance of J10, and the 30 ohm resistor stays 30 ohms. And then my output VO, this little VO, becomes big VO. Okay? That's the phasor transform of little VO. Right? So that's all we've done. We've got the same unknowns, you know, but these are now going to be complex numbers. Big IO and big VO are going to be complex values. We're going to solve for those. And the capacitor has been changed to a resistance of minus J20, and the inductor is now J10. Okay, so that's the circuit, and it can now help you see that. And then, of course, we can add a ground. We're going to use nodal analysis to solve this. So we're going to label these nodes. We can call this node 1 and this node 2. And so step 2 is going to now be to set up the nodal equations, which we should be good at. It's really the same old thing. Just you've got a couple of complex values that are going to be floating around that. So I'm going to change that to red. And so at node 1, what am I going to do? What am I going to write for the equation at node 1? V1, right? Let's call this V1. So V1 minus 10 over 20, all right, plus, yeah, V1. And these are phasor V1s, right? These are actually complex values too. I'm going to draw them like so. So phasor V1, phasor minus phasor V2 over minus J20, right? Yeah, these are phasor Vs. Yeah, sorry. Make these big. Phasor V1 minus phasor V2 over minus J20, and then what else? Yep, plus V1 over 20 equals 0. Okay, equation at node 2. Right. Plus phasor V2. Well, that's true. You could have VO as one of those nodes, but you know it would be another equation you'll have to add in there. And since actually there's really nothing really going on that branch, you could define the whole current going to the right here with just one equation, right? You don't need to say, you could say V2 minus VO over J10, right? Or you could say V2 minus 0 over what? Like if you went all the way to 0 over 30 plus 10J, right? So it's really V2 minus 0 over 30 plus 10J plus 4IO, yeah, equals 0. Okay, and what's IO? IO, actually, I didn't label that on the plot, yeah, so I should have an IO here as well. This is IO, it's the current going down through that 20 ohm resistor. So IO is going to be what? That's just V1 over 20. So we have two equations and two unknowns, right? Except they're kind of nasty equations with complex numbers in them. And that's okay. We're going to simplify them. And my thought is, you know how in nodal analysis you try to like multiply by the least common multiple so you can remove the fractions and everything like that? But you know how many mistakes you're going to make when you try doing that? Because every time you got like a J thing, you got to take J squared is negative 1, and you can have all kinds of sign errors. But you don't have to be as, when you're using FreeMat, you don't have to worry about that. You can just leave it as close as it is to the original, and then just type in all that stuff carefully so you didn't make any transcription errors. Yeah, no. We're not going to do nodal analysis on the next exam. You're going to do the stuff from the assignment, last assignment, the one you're working on right now. Yeah, you can use FreeMat on the final exam. Test 3, you're going to, yeah, probably. Yeah, we'll do it upstairs. So to simplify, we're going to have to simplify this a little bit. So simplify, I guess that's step 3. And to simplify, we're going to say, all we're going to do, this is what I think you should do. You should just take V1, make a big parenthesis, and list all the terms that are multiplying V1. So what am I going to put in those parentheses? Yeah, looking at equation 1, this is still equation 1, yeah. So V1. So V1, sorry? No, I'm going to take, I just want all the terms that are multiplying V1. So what do I have multiplying a V1? In other words, if I break up this fraction here, this is a V1 over 20 minus a 10 over 20, right? So I have a 1/20th multiplying V1 here, don't I?
I thought you were okay.
Right.
So it's one, yeah.
It's 1/20. What else is multiplying V1? Yes, plus 1/-20j. Now, I think it's okay to put that negative from the bottom to the top, don't you? You're not going to mess that up, right? So we could actually say that's minus 1/20j, right? Minus 1/20j. So I'm going to put this here, so it's going to be minus 1/20j, and then what else is multiplying V1? There's another 1/20, right? So you can't let Freemat do this yet. You have to put it in the form for Freemat, and you have to take us to this point. Okay, so 1/20 minus 1/20j plus 1/20 is all multiplied by V1. And now we're going to list all the things that we're going to multiply V2 by. Okay, somebody want to give me one? Right there, what are we multiplying V2 by? V2, you're doing V2 times 1/minus j20, right? Is that what you're saying? Oh, I'm still doing it, yeah, sorry. V2, V2 times 1/j20, right? Good, 1/, I'll call that 20j, 1/20j. And is there anything else? That's it, right? And then it equals what? Yeah, well, plus 1/2, right? Because you're going to move that to the right side. I'm going to just write 10/20 just so people can remember that came from that. And then that one's basically done. Now, I'm kind of running low on room, but the second one, you know, for when we see I0 here, we're going to just plug V1/20 in there. It's a pretty easy substitution, so I'm not going to rewrite that, right? So for the second one, let's take and do the same thing. Let's group all the V1 coefficients together. So V1 times, and then what am I going to do here? I've got a 1/20j, okay, and what else? Now there's still another V1 in there. I see a little more than that, because it's 4I0, right? And I0 is V1/20, so what is it? Yes, or if you want to just be cautious, it's 4/20. So you don't have to simplify, because you know Freemat's going to do all that for you. Whatever's easier. I mean, if it's easier for you just to type 1/5, you know, that's fine too. But I'm just thinking, let's do the least amount of changing so we don't screw anything up, right? And it's kind of easier to track whether you got this all copied over too, right? And then there's going to be all the V2 terms, and all the V2 terms are what? Yes, we've got a minus 1/20j plus. Think again. Yes, plus you got to do the whole denominator. Plus 1/30 plus 10j. Okay. Anything else? V2 ones? I think that's it. And all that equals what? 0. Okay, this is as far as we have to go. At this point, you just go to Freemat, and you let it do the rest, or MATLAB, whatever you have. Okay, you've got it in matrix form, and this is what MATLAB does really well. Okay, and so on the lecture slides, these are not on your handout, but this is what you would actually type to solve it. Okay, you would actually type in, you get all the coefficients and make a matrix of the coefficients, and we call that A usually. So A equals, and here I've just lumped, you know, 120 plus 120 to call that 220. So I've got 220 plus J20. Wait a minute, did I make a mistake? 220. Oh yeah, 1/20j. I was thinking too hard. So 1/20j, if you multiply that times j/j, becomes plus 20j, right? Minus 1/20j becomes plus j/20. Wait, did I do that right? Yeah, that just becomes j/20, you see? But I don't know if that's a good step for you to make. I think I should have just left this as minus 1/j20. But you're going to have to use parentheses if that j is in the denominator. Otherwise, you know, if you just write minus 1 divided by 20j, it's going to be 0.05j. The j comes back up on top, unless you put it in parentheses so it's in the denominator. Should I say that again? In other words, if you type minus 1/20j, this is actually something you kind of have to be worried about, because the order of operations, although that's 20j, you know what? Let me, I always have to, I'm never quite sure about this, so I'm usually cautious and I put parentheses around it to make sure that j stays in the denominator. I know on my calculator, if I just wrote 1 divided by 20j, the j would be on top. It would be 1/20th of a j. not 1 divided by all 20j on the bottom, right? So let's see what Nodal does. So 1 divided by 20j, j gives me, I think it did it right. Minus 0.05j would be the right answer. It's the same thing as 1 divided by 20j, right? But on my calculator, that would have said 0.05j. So that would have flipped the sign on me. So actually, you're okay. You don't need to worry about that. I continue with the second row, and well, actually, so it's see. And what I'm doing is, so there's 120j there becomes minus j over 20. I'm putting commas between the different, because these are actually can be pretty long expressions now. I'm using parentheses to make sure those are grouped properly, and I'm separating them by commas. Semicolon means go to a new line, and then the next line has this stuff and this stuff. That's all that. So that's my A matrix. My B matrix is just 0.5 and 0. And then to find the answer of the unknown V's, which is going to be my V1 and V2, is just A backslash B, as we talked about yesterday in lecture. And so V is 1.4356 minus 0.6436I. And that's V1. That's the voltage at that node. And the voltage at node 2 is the second line right there. Okay? Now at this point, you can just take and solve, because we're actually trying to solve for VO. And VO is just a voltage divider of V2, isn't it? So VO is just 30 over 30 plus 10J times V2. And you can specify V2 as being V parentheses 2. This V is a vector. V1 is the first voltage. V2 is the second voltage. So V2 times 30 over 30 plus 10J is going to give you the answer, which you can then convert into polar form, like so. But you know, at this point, if you just want to take these numbers back into your paper with a calculator and just continue it that way too, you can do that. But it's a lot easier just to finish it off. So that's the answer, because we found the polar form of VO. So that means VO of t is 6.15 times the cosine of 1,000t plus 70.3 degrees. And then, you know, you got to wonder, is that right? How do you know if the answer is correct? No, you go to the grader and type it in and see if it says it's correct or not. But you should be able to know. So I did a check, and what I did was I thought, well, let's check if KCL at node 1 still holds with these values of V1 and V2 that I solved, right? In other words, that first equation, because I might have made a sign error in this A matrix. You know, there's a lot of ways just getting from, you know, setting up the equations to just getting from this step to this step, and then typing it into MATLAB, and then, you know, expressing the solution. You might have made some mistakes. You know, you got to be honest. That can happen. Yeah, right? Oh, I just deduct points. Yeah. You know, my dream is on the final exam for circuits, I just give you one problem, and your score is the percentage of how close you are to the answer. It's inversely proportional to how far off you are. That's my dream, but I don't think I could actually do that. Yeah. So that means you got to figure out how to check to see if your answer is correct. And one way to do this in nodal analysis is to do one KCL. If we do KCL at node 1, if that holds, then we can be pretty sure that we got the correct answer. So I'm going to take my solution for V of 1 and for V2 and plug it into that formula, and I'm doing that right there in FreeMat, so I can just verify it right there. V of 1 is V1 minus 10 divided by 20 plus V of 1 divided by 20. I'm just typing in that same equation, plus V of 1 minus V of 2 over minus J20 equals, is that 0? Wait a minute, is that 0? What's wrong with this? Is this 0? Is that, well, isn't 10 to the minus 17 close enough? No. That's round off error, right? So that says 0 to me. 10 to the minus 17 is really small. Okay, that means we got the right answer. We can rest assured that we did it right. Okay, and that's a good feeling, and it's not that hard to do in FreeMat, just to take that, you know, one more time. Take your solution and plug it back into the original equation and see if it's still fast. Yeah, well, I don't think, yeah, I think you'll be fine. You might say a little rounding error. All right, so we spent the whole class doing one problem, and that's kind of how it goes. Example 2 is another nodal analysis problem, but I don't know if we really need to do this. maybe we'll save this and come back to it for a problem-solving session later. Example 3 goes into mesh analysis. And those people might be coming in at any time, so we might have to interrupt. But let's just sort of think through the beginning of this problem, looking at the circuit, and kind of see how we go. And I've actually, to save space and time, I've actually put the MATLAB things that you're going to type in right here to get the answer. But we have to drive the stuff that comes before that. So this is a mesh analysis circuit that we're asked. We're asked to use mesh analysis to find the voltages. You know, I was going to change this. I guess I didn't change this. I was going to have it just find I1 and I2, and I didn't. Yeah, just change the question to say I1 and I2. And let's define these. Let's define them the way I've got them here. So yes, we're going to call this the thick I1 and the thick I2. Or IA and IB if you prefer. I like IA and IB as well. But we're going to call it I1, I2. And so if we're trying to find those guys, what are we going to do? Oh no, I actually did take it all the way. Sorry. Don't scratch that out. We're going to find them. We're going to find V1 and V2, but we're going to find it using I1 and I2. Anyway, we're not going to have enough time anyway. But so let's just kind of go a few steps down here. So what do you see here? What kind of approach are we going to take to solve? First, we're going to solve for those mesh currents, and then we're going to use those mesh currents to solve for V1 and V2. Well, before we do that, look at what you got there. What kind of circuit? There's some special case mesh circuit topologies, right? Does that look like anything you should be thinking about? Mm-hmm. Oh, actually, you don't. In fact, this last circuit still has, it's giving us a sign. We know omega, and this is example 2. But in example 3, they've already done the transform for us, and all of these things here, they're already transformed into these complex values. And all we got to do is find the phasor form of these guys. Okay, so, all right, let's just start the mesh equation. Okay, so what are we going to say? Somebody? But let's do everything in terms of the mesh currents, because that's going to be the better representation for this, right? So what are we going to say here? So we'll start in this corner, okay, and just go clockwise. So we're going to say what? Yes. I'm going to write it J2I1. J2I1, okay. And then what? Yep. Minus J4I1, okay. Then what? Okay. Sorry? Say again. So what do I want to write? Do I need to write something here then, or what? So Christian is saying to do what? What do I want to say here? I want to say what? Plus, yes, 5 by 2, right? So what kind of mesh equation is it? It's a super mesh, yes, good. It's a super mesh, so we can, yes, we're going all the way around the whole thing because we can't go through that current source. So 5 I2, and then what else? What's the last part? Plus J3I2 equals 0, okay? And then you did say the constraint equation, but let's, I2 minus I1 equals 10 angle 0, or just 10. Mm-hmm. Oh, I don't know. Yes. I don't think you can type J2. You have to type a 2J. But you see, notice how the circuit's been labeled J3, J4, J2. So I'll sometimes just copy that. I think it's, I don't know, either one. Yeah. Okay. So to simplify, again, I've got to get this into a form for free mat. I'm going to group all the things multiplying the I1 term on the first equation, right? So that's going to be I1 times what? I'm just doing the first equation. This is the first equation, and this is the second equation. So the first equation, simplifying the first equation, grouping all the I1 terms, I'm going to have I1 times, all together, times, sorry? Which is? Yes. So we can do some simplifying without making mistakes. I think I can trust myself to do that. Plus all the terms multiplying I2 equals 0. Okay, and equation 2, in the form that we would kind of plug it in from MATLAB, we have to do something times IA, something times ID equals something. So what would be the thing times, or I'm sorry, something times I1? What would be the thing times I1? I1 times this equation, this constraint equation, I1 times, yep, plus I2 times, yep, equals 10. Yeah, right. And now you can plug that into, what, the number 10? The second line is the constraint equation rewritten. And I'm rewriting the constraint equation in a form that meets the matrix solution that I have to set up for MATLAB. Right? It has to be something times I1 plus something times I2 equals something. And the constraint equation wasn't written that way, so I'm just rearranging it a little bit. It's minus 1 times I1 plus 1 times I2 equals 10. And now, you know, you don't really need to do much. You just turn your friendly FreeMat program and type in this. And that gets you the solution for IA and IB. And if you want to see it in polar form, you say mag phase of I. You give it the whole solution vector, and it gives you the two numbers in polar form. Yeah, so you have to download that from the website. Put it in the folder that you're working in, and we'll do that in the lab again so you know how to do that. Yeah, then you would have to use that ENGR function. That's the other thing we played around with last week in lab, right? You could say 10 times ENGR parentheses 45 if it was a 45-degree angle. It does that for you. That's what that ENGR function does. You remember that, right? Yeah, so you would actually just type, if it was instead of typing this, which you're welcome to do, but it's a pain, you could just type 10 times ENGR at 45. And then the last step is to then take those currents and now solve for the phasor V1 and V2. So phasor V1 is going to equal what? Okay, but how do I get there? So how do I derive a V1 from my solution for I1 and I2? What's V1? If I know what I1 is, now I have to write an expression for V1. Sorry? Oh, come on. It's just Ohm's law, right? So I1 is flowing this way. V1, the polarity though is this way, so Ohm's law says V1 is what? Yeah, keep going, please. Oh, come on. You know, those high school students are going to blow you guys away. Yes, it always makes sense after you hear the answer. But you have to make it make sense before you hear the answer. Okay? And so you just multiply your solution for I1. This is I1. This is I2. So it's minus J2 times 11.43 angle minus 160.4. And you'll get the answer.
I saw a bus, a school bus go by.
Oh, that's probably done. Yeah, they're a behind schedule. You know how these things go.
Yeah. I think they're going to the other options as well.
Oh yeah, they're going to do a whole tour of the campus. So anyway, that kind of wraps it up. So V1 is 22.9. If you might multiply that out, it's 22.9 angle 110, and you can do the same thing for V2. V2 is just 5 times I2, so it has the same phase angle. You just change the magnitude. So it's 5 times 3.92 angle minus 101, which is 19.6 angle minus 101. Yeah. Well, next week we're going to do Thevenin equivalent with dependent sources.
Is it on the right room number?
I think so. I'll check my email. But they were going to have someone giving the speech first. You know how if someone's going to talk about something, it always goes twice as long anytime someone says anything.
We have tours at MPS all like every week, and they never come. Like we'll be just sitting around, dressed up, and getting nothing done.
Yep.
All right, I'll have a good weekend.
Yep. No, they're probably in lecture 4 and 102. Okay, see you later.
Yeah, bye, Tom. No?
Oh, check it. No, it's all extras. Okay, later. Yeah, they want to get out of here. Oh, you do? In physics? Really?
Yeah.
Maybe that's where the $5 came from. Give it to me. I read it lost and found on campus.
Oh, hey, Bob. Okay, have you
Yep.
See you next week.
Yep. Okay.